Hi all, this is section 1.10 on predicting molecular geometry using V-separ theory. This is something that you've gone through hopefully in general chemistry, and it's something that we just need to touch on a little bit in order to make sure that we're all in the same place. And in fact, we can use what the book has because they have much prettier pictures than I can draw. So first, let's look at tetrahedral geometry. This methane molecule has 109.5 degrees between each of its hydrogens, just like we saw when we talked about the sp3 hybridization from before. This tetrahedral arrangement is what we'll see for carbons with single bonds, or carbons with all single bonds, nitrogens with all single bonds, as well as, I guess, if you count the electron lone pairs, also oxygen with single bonds, and some others too. So then also we have the trigonal pyramidal geometry. And this is where nitrogen is. Sorry, it's not in the tetrahedral. In trigonal pyramidal geometry, you have 107 degrees between each hydrogen, and they're pushed down a little bit because the lone pair on the nitrogen is so big. Even so, each of these sp3 hybridized orbitals that's attached to the nitrogen is very similar to the carbon sp3 hybridized orbital we saw above. It's just that this lone pair really serves to push down the rest of the bonding orbitals, and which is why there is a shape change there. We'll also go over bent, which is what you'll see for oxygen here. Oxygen, if you're just counting the atoms, has a bent configuration because it is in this not linear form. But if you take into account the electron lone pairs, then the bond angles are around 105, which is very similar to the tetrahedral arrangement we saw for CH4. So we would call that sp3, or we would call that a tetrahedral arrangement with all the lone pairs included. They do have much nicer pictures here than I can draw. And last, we'll talk about trigonal planar, which is shown here with this BF3 molecule. In trigonal planar arrangement, you have all of the atoms sitting in one physical plane. We are seeing this, or we're seeing a vertical arrangement, but if you were to turn it on its side, they would all be in the same XY plane. And there's 120 degrees between each of these atoms. Okay, and last, there is linear arrangement, which they're showing us with this beryllium dihydrogen molecule. That's kind of a funny molecule to include, but it at least lets you see that there are some cases where you have a full 180 degrees between atoms. All right, so you can look at table 1.3 if you need a refresher on the steric numbers and predicted arrangement of electron pairs versus molecular geometry, just like we learned in general chemistry. And this has been section 1.10.